Hello, everybody. This is Charlie Belfontaine, and I am going to do a full all out electrical presentation on a checklist that we created with the International Association of Certified Home Inspectors, more specifically, InterNACHI School. I'd like to take a few moments and just introduce myself right now. Again, my name is Charles Belfontaine, but I go by Charlie. I am the owner of Chicagoland Home Inspectors, and based obviously in the city of Chicago, and we service the entire Chicagoland area. I started inspecting houses in 1993. I am a NACHI home inspector. I also do a lot of field training for their online program here in Illinois. I am a training partner for NACHI. I'm also a certified master inspector and certified professional inspector. I've been training home inspectors since 2001. Chicagoland Home Inspectors is a multi-inspector company, and I'm also a member of the Home Inspection University. Right now, I'm also the president of the Illinois Association of Home Inspectors, which we started in 2019. It's a lobbying group that we work on making changes to the home inspector law and rule here in the state of Illinois. All right. So first of all, I just want to start off with safeties. And again, this inspection checklist is going to be available in the links below this YouTube after everything is done and presented. So we're going to go back and edit all this stuff as well. But electricity is a pretty serious thing. It bites. People get hurt, and it actually can kill you. So let's be a little cautious with it. I'm going to hit a few safety devices or safety items that we should think about. Number one is going to be eye protection. What happens whenever there's a short or something inside of an electrical panel, that those wires are actually going to create sparks, and those sparks are basically molten metal that's flying in the air. We just see them by glowing. And God forbid any of that stuff gets on your clothes, your eyes, your hands, whatever the case is. So we want to go ahead and make sure that we're protected, whether it's face masks, gloves, breathing equipment, anything that's not conducive to electrical flow. And then also keeping rubberized soles on there, staying out of water, and keeping other people away from you as well. All right. Now, every person is different, and your knowledge and experience is different. All right. Don't try to push it. There's nothing wrong with gaining more education and learning more that you could do. And in the NACHI classes, they got some great materials. Just keep taking those things over and over again. We all pay for knowledge, whether it's the College of Hard Knocks or whether you use this NACHI membership to benefit you. All right. And don't do anything that you're not uncomfortable doing. I actually like these signs that NACHI sells through their inspector shop program. Setting those up, kind of telling people to stay away from you so they don't get close. And again, don't use the wrong tools. I want to say don't do what I do. All right. So this is going to be one of those goose and gander things. So, when I'm short, if I don't have the right screwdriver or something like that, I'll grab a quarter or something, and I'm just going to do something totally wrong. I cannot encourage anyone to be as dumb as I am, so please don't. All right, we're going to go through the standards of practice. I know there's a whole bunch of words up here. I am doing this on a YouTube live channel right now, so if anybody does have any comments or if anything to add to it, type them in. I am watching those comments, and I'm more than happy to answer them here. So a few key words that we're going to pop up here when it comes to the standards of practice, and this is the NACHI standards of practice. Most states will have their own standards of practice that they have to abide by. But if you're a member of NACHI, they want you to be able to abide by these too. So keywords that we're going to see on these standards is going to be the word inspect, the word describe, the word report, and then there's a phrase that basically says the inspector is not required to. So we're going to hit all four of those sections on the electrical portion. And when you see that it says inspect, and we're looking at what's right here. So the inspector shall inspect. And we're going to look at is what they're saying. The service drop, the overhead service conductors and attachment points, a service head or gooseneck and drip loops, the mast, the service conduit and raceways, the electric meter and base, service entrance conductors, the main service disconnect, panel boards, overcurrent devices, includes both the breakers and the fuses. We're going to talk a lot about grounding and bonding this morning. A representative number. This is another good word to find the definitions in the standards, and it is there. And basically, in a nutshell, representative number means one per room, and that's a minimum. There's nothing that says you can't do more. Or if you're on outside walls, it's one per exterior wall. That's the minimum that we're supposed to be doing. So a representative number of switches, lighting fixtures, and receptacles, including receptacles observed and deemed to be arc fault or AFCI testers, and protected using the AFCI test button where possible. All right. All GFIs and deemed to be GFI using a GFI tester where possible, for the presence of smoke alarms and carbon monoxide alarms. So those are the things that we're going to be inspecting. Now we shall describe, and this we have to put in writing in our reports. The main service disconnects amperage rating, if it's labeled, and the type of wiring observed. One thing that I think used to be on here was determining the voltage. And there's some well, I'm not sure about association, but I know our state of Illinois does require the home inspector to put the voltage of the system in there. And that might be something we're going to work on removing because, in all reality, we don't know the exact voltage unless you put a voltage meter on it. I mean, we could take guesses at stuff by counting the wires, and I'll talk about that in a little bit. But all in all, that is not one of the mandated things that we have to do. Now, I'm going to go into greater detail about determining the actual amperage as opposed to just documenting the amperage that's on the circuit breaker, because I'm a big believer of knowing more and, basically know as much as you can when it comes to this stuff. All right. The inspector shall report as in need of correction. Now, this is something that I applaud Nachi for. We should be coming down to what's acceptable and what's not acceptable. Now, they're not going to the point where they're telling you what is acceptable, but they are saying, hey, if we run into these things, then we need to document it, period. So deficiencies in the integrity of the service entrance conductors, also known as the SEC, any sort of insulation on the NEC, drip loops, vertical clearances from grades and from roofs. Any unused circuit breaker panel openings that are not filled. The presence of solid aluminum branch circuits. So solid aluminum branch circuits, if readily visible. All right. So we are going to talk about the different types of conductors we're going to find in the electrical system so we can help you identify those. I am going to want you to know the difference between a branch circuit and a feeder circuit. And I want you to know the difference between a solid conductor and a stranded conductor. All right. Any test of receptacle in which power was not present, polarity was incorrect, the cover was not in place, the GFCI devices were not properly stored or installed or did not operate properly, evidence of arcing or excessive heat, and where the receptacle was not grounded or was not secured to the wall. And then also the absence of smoke and carbon monoxide detectors. Here in the state of Illinois, we're going to take that one step further because in Illinois, we do have a smoke alarm law and a carbon monoxide alarm law. And we're going to be changing our rules so that we have to report or document if smoke alarms or the building does not comply with either the smoke alarm law or with the carbon monoxide alarm law. According to the standards of Nachi, however, you only have to report on the absence of the smoke alarms and the carbon monoxide alarms. Now, this one here, the inspector is not required to. I hear a lot of my fellow inspectors say that we're not supposed to do that. And that is not what this is saying, all right? It just says you don't have to, all right? There's nothing wrong if you want to learn how to do it and you want to do more, be more, and charge more. There is nothing wrong with that whatsoever, all right? So, we are not required to insert tools, probes, devices in any panel board or sub-panel or any fixtures. We're not required to operate electrical systems that are shut down. We don't have to remove the panel board cabinet covers or the dead fronts, all right? This is something that I don't believe in. I think we should be taking those dead fronts off and getting to look on the inside of them. I'll agree with the first ones, about not using something that's shut down. I don't know why it's shut down. And if me turning power on energizes something and then all of a sudden it starts a fire, that's someone else's problem right now. But by me turning it on, I end up making it my problem. And unless you're intimately familiar how to use the right tools and and have the proper protection, I gotta agree 100% with the first one. Don't go poking stuff inside that panel, all right? But as far as the visual inspection, I want to see inside that panel. And that's me. I'm not encouraging anyone else to do it, but I am going to share what I do. Operate or reset overcurrent protection devices or overload. Exactly. Operate or test smoke or carbon monoxide detectors or alarms. I could tell you a quick story on that one. I used to do it, and I learned the hard way when the fire department showed up, because I thought it would be a good idea to put the smoke spray in there, and then the alarm system in the house decided to notify the fire department, and they came by and interrupted my inspection. How rude of them, right? Inspect, operate, or test any security, fire alarm system, or components. If it's over your head, it's over your head. If you want to learn about it and offer it as a service, there's nothing wrong with that. Measure or determine the amperage or voltage of the main system. All right, kind of what I was mentioning beforehand. We don't even have to document the voltage of the system anymore because it's not in the standards. Inspect ancillary wiring or remote control devices. Activate any electrical system or branch circuit that is not energized. I think we saw that before. Inspect low voltage system, electrical de-icing tape, swimming pool wiring, or any time control devices. All right. And again, if you want to learn about this stuff and add it to an extra system, there's nothing wrong with doing it, but you're not required to. Verify the service ground. This one I'm going to disagree with. I think we should do our best to identify and verify the service ground. However, I do believe the reason why this is here is because sometimes that GEC, the grounding electroconductor, goes behind walls and we're not going to be able to visually see it and verify it at one end to another. But if you can, I think it's a very important part of what we do. Inspect private or emergency electrical supply sources, including but not limited to generators, windmills, solar systems, battery or electrical storage facilities. This is another one I got my guys and myself. I'm trying to learn as much about these things as I can right now. And we are going to be including those, maybe not with our inspections, but we would be charging extra for them and create a whole section in our report for it. People are going to be buying these things. They're going to be part of houses. They're coming more and more as it's there. And now we're running into these things when they're being resold. So determining the age, lifespan, and what these things can get out of it, the more we learn, the more we know, the more we're worth. Inspect spark or lightning arresters that you find on roof, de-icing equipment, conducting voltage drop calculations, and making this one kind of clear is a little bit important. And this has not happened to me, but where I've seen this happen to people in the past is where, like these Peloton bikes, they require, a certain amount of amperage and a certain amount of voltage. And if that circuit is so far away that you have such a voltage drop, they don't work properly. All right. Now, I haven't had that complaint yet, nor do I do voltage drops on my testing. But realize that could come back and you need to be prepared for that should somebody complain. So determine the accuracy of labeling. And this one, I can't tell you how many times it's wrong. People end up, they'll either change a circuit or they'll write the wrong thing on the door. We don't follow them. I just see that they're labeled, and that's about the best I could do. I think it would take a long time if you ever really try to go forward and label everything. And the last item on here is going to be exterior lighting. And I'm not too sure on that. I mean, we do include that on ours, but I'm talking about the lighting that's attached to the house, like porch lights and stuff like that. But I've run into some high-end homes where there's up lights going into trees, lights in trees shining down, stuff all over the landscaping is in there. And I mean, that's an artwork in some of these homes when they put the gardens and the lights and the sprinkler systems in there. I mean, we do try to turn them on and check to see that everyone is there that's working. But let's be realistic. I might not be able to see one that's inside of a bush and miss it, and I don't want to be in trouble in case it's not working. But I'm going to do the best I can, plain and simple. All right. Kind of what I was mentioning a little bit earlier. Know what you're talking about, right? And I think that's the biggest problem here is, most of us were able to get a 70% on a multiple choice test, and we're helping people with the biggest purchase of their life. And I know this sounds arrogant, so I am going to ask for forgiveness in the beginning, but that's not good enough for me. All right. Somebody is spending every amount of money that they have to buy this thing, and we should be able to get them as much information as we can. So the more we know and the more we learn, and talking intelligently and communicating intelligently is vitally important. So this whole comment right here, when I start hearing that home inspectors are thought about being dumb, your home inspector doesn't know what he's talking about from the electrical contractors. A lot of that's true to a lot of people. I just don't want it to be true about me. Nachi has done a great job, all right? They end up creating their SOPs, and they got some great training facilities or great training stuff online that you can go ahead and read, and it's all free for us, right? So their definitions, I think you can find all of those in the electrical class, their inspection articles, their YouTubes, everything's there, so take advantage of as much of it as you can. And this is just going to be one step that we're working on here. All right. I want to focus on 4 main words. And these words, I do want you to know what they mean. All right. And if it's basic to you that you're listening, please bear with me. If you don't know this, screenshot this thing. Get to remember these words here because they're vitally important. Anytime you see or hear the word current, they're talking about amperage. All right. Amps, and I like one-word definitions. I love them. So amps, that means current, all right? It really means it's the flow of electrons and measured in amperes or amps. And that sounds all confusing as all heck to me, all right? And I have trouble with that. So for me, I want to remember a few things about amperage. One is it basically creates an electromagnetic field. It doesn't really move, all right? So as the amperage is created, and let's say that this dot right here is looking straight down the conductor, it's going to create a little bit of a glow going around there. And the more watts that I'm using and the volts that comes into the math, the bigger this circle is going to be. And it's going to keep getting bigger and bigger and bigger, right? Now, amps also does not disappear, all right? Let me go ahead and write that down because that's important. Does not disappear. Oops. I know I spelled that wrong, I'm guessing. Amps does not disappear. It ends up, in other words, if I got 5 amps flowing on the energized conductor, I will have 5 amps measured on the neutral conductor, all right? Now, they will cancel out, mind you. If I have a 240 volt circuit, so let's say I got 3 wires coming in. So 1, 2, 3. And let's say this is my neutral here. And this is my first energized. So that's 120 volts. This is 120 volts. If I have 5 amps flowing on this one, and I have 5 amps flowing on that one, since these 2 wires will always be 180 degrees out of sync of each other, when this one is a positive 5, this one's going to be a negative 5, all right? So when I take positive 5 and I add negative 5 to it, guess what I'm going to end up having? I'm going to have 0. And that's why you're going to find on central air conditioning systems, electric radiant baseboard heat, as long as it doesn't have an outlet built into it. You'll find it on well pumps. Many times, they're not even going to have a neutral wire. They're only going to have 2 energized conductors. And the reasoning is, if I don't have any amperage flowing on that conductor, I don't even need it. And that's true, all right? It doesn't really count when we're dealing with electric dryers or electric stoves, mind you, because those have little light bulbs in them, right? So those little light bulbs, they may take 1 amp. So that means I'm going to have 6 on this side, -5 on that side. Now when I add the two together, I'm going to have -1. I need that neutral wire to bring home that -1 amp or that 1 amp that's left over between the two of them. I'm hoping that makes a little sense. Voltage is the pressure. I like to think of this as a magnet. The more powerful a magnet is, the more electric push it's going to have, all right? Those high tension wires, they are pushing electricity at tremendous amounts of voltage. The transformers that we see on the poles in our neighborhoods, those are actually knocking it down to 120 or sometimes 240 volts, which is what we normally use inside of houses, all right? The little trick on these things is using the numbers, and it goes back to the slide beforehand, saying the right terms. I really don't care if you're going to say 110, 115, 120, or what you'll see in code books, 125. What I do care is that when we're talking about a single phase 120/240 system, that you double these numbers. So if you're going to say 110, then you're going to say 110, 220. You're going to say 150, 230, 120, 240, or 125, 250. And we should be consistent on using the proper terms when it comes in there, all right? But as far as measuring the voltage in itself, that's just not something we do. Watts, that measures in power. So that's the one word I want you to remember. And I like to remember it by saying we pay for power. So I keep remembering the P's that are involved in there. So watts travel at the speed of light. They go to wherever the work is being done, and then they change into something else. So if we put our light bulb back up there again, that watts are going to be traveling to our light bulb, and then it's going to be changed off to light, and then also some heat. And that's it. It's gone. It went to the light bulb. It did its work. I want you to remember that word as well. It did its work, and then it disappears. It does not come back on the neutral like the amps do. Amps are going to be present on both the energized conductor and the grounded conductor. The grounded conductor is the proper name for the neutral. Ohms is measured in resistance, all right? Going back to our light bulb that I have back up here, I'll just draw it a little bit bigger, all right? And that. So what happens is when that wire comes in, it's going to take it to a filament here, a very thin little wire. And that thin wire, that thin filament, slows down the electricity. It limits the amount of electrical flow. And then on the neutral side, it goes back. All right. Now, if I took this energized conductor and I touched it to that neutral conductor, I don't have that filament to slow that electricity down anymore. Whatever's available on the grid will attempt to flow far more than what those breakers are allowing to flow. So those breakers that measure in amperage, because it's going to create this big electromagnetic field, that amperage is going to flip and turn the power off, plain and simple. But that's a good thing, because what it did was it made our electrical system safe. The whole idea is we don't want anybody to get hurt or bit, so when electricity is doing something that it's not supposed to be doing, we want to go ahead and shut that power down as soon as possible. So let's talk a little bit about conductors and different types of materials, all right? What we're showing over here in the middle, this is an aluminum wire. I mean, it's simple. You can see with the silverish color that comes to it. But it's also a stranded conductor, as opposed to the copper solid. So we don't have a bunch of strands like we do between the aluminum one that comes in here. I also want you to know another word called cladded or cladding, all right? And here, and cladding means that I'm wrapping something around something else, all right? In other words, if I had a wood window and I wrapped vinyl around it, that would be a vinyl cladded window, all right? In this case here, I have an aluminum wire, but I wrapped copper around it. So that's copper cladded aluminum, all right? And maybe this statement that I'm about to say isn't 100% true, but it pretty much is, all right? It's pretty gosh darn close, and we're going to treat these wires as the same. Electricity, that wattage, flows on the skin of the conductor, all right? So it doesn't matter what the middle's made of. It matters what the outside is made out of. And if the outside's made of copper and it's the same size as a solid copper wire, believe it or not, that wire is going to have the same conductivity, even though it's mostly aluminum and the other one's mostly copper. So why do people do this? Aluminum is a hell of a lot cheaper, all right? So if they can make a process where they use a lot less copper and more aluminum, then they could get electricity or electrical wires for a lower cost. And in our society here in the States, our home buyers want the biggest bang for the buck. So home builders want to build as much square feet and give the biggest home that they can, but they still want to make it as cheap as possible so that we can give that big American dream to everybody and not just the rich. Another material that's going to find in older houses, and you'll find these in houses built post World War II, but mostly it's going to be pre World War II. All right, and this is called tin cladded copper. All right, and basically it's going to be a copper wire, and then they're going to have a tin cladding, just like we showed the copper cladded aluminum before. It's going to have a tin cladding. The dead giveaway of this is going to be this cloth jacketed insulation. All right. I am not aware that these wires were ever manufactured with plastic insulation. We really don't use tin for cladding anymore. You know, copper seems to be the preferred metal of choice that comes into it. You know, so even though this does look like it's copper, I believe it's because the tin was worn off of it or rubbed off of it. If this looks like it's a silverish conductor with the cloth insulation, that is tin clad copper. So identifying the conductor materials, I do believe that is part of what we're supposed to be documenting, and we should be able to recognize it as well. A lot of people have problems with this stuff, and here in Chicago we use a lot of conduit, you know, and they actually call us a conduit city. But what happens with this cloth jacketed in the conduit is it dries out and it gets brittle. And then what you find out is when you go to change a light fixture or a switch or an outlet, and you start bending these wires, that insulation basically comes free and it deteriorates. So, yeah, I don't know what much more to say on that. The good news is it's in conduit, so if it does get, you know, all cracky and falling apart, at least we could pull it out and put the new stuff back in. And that's one of the glories of conduit, is you can actually replace the wires and you don't have to break open the walls in order to do stuff like that. So tin copper versus bare copper, these are both stranded wires, and again, I'm just not aware of anybody still manufacturing tin copper today. Not saying that it doesn't happen, all right? So we're going to start our electrical inspection, and we're going to start on the outside, all right? I do want you to know a couple of terms. One of them is called a service drop, and the second one is called a service lateral. In a nutshell, in simple speaking, if it comes from overhead, it's a drop. If it comes from underground, it's a lateral. And it's really that simple. We are expected to know the different clearances around walking areas. We saw that, you know, it says what we have to inspect and document. Roofs, windows, you know, secondary buildings like garages, walkways, driveways, alleyways, pools. We'll get to all those in a little bit. All right. So typical cable assembly that comes into the house is going to have 3 current carrying conductors. All right. And again, I use the term current, and whenever I use the term current, I mean amperage. So all 3 of these wires are basically going to have some form of electricity flowing on it. We're going to call that amperage. The 2 wires that are insulated, those are going to be the energized current carrying conductors. The one cable that is not insulated or has no insulated on it, that's going to be our grounded current carrying conductor. The term grounded current carrying conductor, I've used this before. We're going to use it as neutral. All right, so that's going to be our neutral wire. When we're dealing with the overhead service, this is also known as the messenger cable. The messenger cable. And we're talking about this one right up in here, where this red arrow is pointing as well. All right. That actually supports the other wires, and that's where the main clamps come into, but they all work together, all right? And then they're twisted and tied. So if each one of these carries 120 volts, and this is a single phase system, then when I measure between 120 and 0, I'm going to get 120. When I measure the other one, 120 and 0, I'm going to get 120. These 2 are going to be opposite. So when that's negative, this is positive. When I measure between the 2, that's where I get the 240 from. So when one's pushing, the other one's pulling. They offer 2 directional force, so a negative magnet and a positive magnet. And one's going to push stuff away, one's going to pull stuff toward. And then I could use both powers at the same time to double the force of the electrical current that I'm getting. Cool stuff. All right. And forgive me if I get a little hyper about this stuff. I get passionate about building sciences. All right, if you don't have these numbers memorized, you do need to take a screenshot of this. You could also download these graphics at the Nachi website as well. They're all free for all members that are on there. And it's a great thing to add to your report, all right? Some people like to use the code check graphics. I'm not against those as well. But the one thing that Nachi is doing is they're trying to make sure that their information is extremely accurate so that if you are going to be using these documents in your report, they're not going to hang you out to dry, all right? So I really trust them, and they do get all this information from the code books, even though you hear a lot of people saying, don't quote codes, don't quote codes. You know what? It's always good to have something to back your opinion up, something with some validity. And I'm very happy that Nachi's taken that stand on what is acceptable and what is not. So let's start with walk areas first, all right? So whenever we walk, now that doesn't matter if it's a sidewalk, if it's grass, if it's a deck on a roof, if it's a flat roof with walking surface to it. If I got power lines over an area where a human being can walk, I need to have at least a 10-foot clearance. If it's on a driveway for a house, that's got to have at least a 12-foot clearance. And going back to the 10-foot mark, just, we're not going to throw tape measures on there. You don't know if there's some, damaged insulation and you're going to be standing on the ground and now you're going to be touching something like that. You don't know. So it's going to be a rough estimate that's going to come into this. A basketball hoop is 10 feet off the ground, all right? So I like to use the rim of a basketball hoop as kind of my comparison, all right? So I got a rough idea about how tall a basketball hoop is, and that's going to be 10 feet so I can see if I got enough clearance, all right? Driveways, 12 feet. Roadways, alleyways, those are all going to be 18 feet, all right? Now here they say 8-foot clearance for a roof, 10 foot if a balcony is in there. But again, it all depends what that roof is being used for. So in other words, we have flat roofs in Chicago here a lot. They put mechanical equipment up there. And those flat roofs, if you have to climb out there on a window and get on the roof, if you have to put a ladder on the roof to get up there or climb up through a hatch to get up there, then it's 10 feet. I'm sorry, then it's 8 feet, all right? But if there's what we call dog houses in our area, so in other words, there's a staircase and a doorway that leads out to that flat roof, now I'm inviting people to go out there. If somebody puts furniture, a deck, or something else in there, and a staircase that goes out there, that ends up being now a 10-foot clearance. So I don't know where the balcony stuff came from. That one I might question a little bit, but I want you to know how the walking space is being defined. If it's mechanicals only, and people only go up there to service the mechanicals, then the clearance is 8 feet. If it's where human beings are going up there to entertain, or they're expected to go up there, invited to go up there, then it's going to be 10 feet, all right? Swimming pools, basically anything within 10 feet of it has to be 22.5 feet high, all right? There's no ifs, ands, buts about that. If it's further away than the 10 feet, then it goes under the other rules of, 10, 12, 18, whatever it is. If it goes over another roof or another building, that's where this 3-foot mark comes into play, all right? But that's 412, and I guess that is a good point. So for what we're talking about with flat roofs, anything under 412 is considered a flat roof, and that's when it has to be 812. Sometimes you're going to see a service mast come up and the wires come over the roof like that. Sometimes this is 18 inches and sometimes it's 3 feet. It all depends on the horizontal run over the roof. So if the horizontal run is less than 4 feet, then I could be within 18 inches. If it's greater than 4 feet, now I have to be a minimum of 3 feet over the roof. So if we look at this attachment here, compared to where the roof comes in there, either this is a very small house, or that's going to be by relation more than 4 feet of a run overhang. So that wire has to be at least 3 feet above the roof. So as it's drawn in this diagram, where it meets and comes into the roof, that's no good. It has to have a service mast that comes up and raises it up by at least 3 feet. Good stuff. All right, this is in writing, and again, this was all taken from the code books, all right? So if you don't have these memorized or you want to keep a cheat sheet with you, again, screenshot this, all right? Nachi did a great job getting this stuff for us. So public street, roadways, alleyways, parking areas with truck traffic, 18 feet. Commercial parking areas, 18. Pools, 22 and 6 above and 10 horizontally. Over residential properties, yards, driveways, everything else, parkways, 12 feet. Over walkway areas, sidewalks, deck, roof surfaces, 10 feet with the lowest point. Above roof surfaces having a slope less than 412 but not subject to pedestrian traffic. All right, and that's where that inviting people out there is. 8 feet. Roof surfaces having a slope 412 greater 3 feet. And then again, that has to do with a separate building. Over roof surfaces where voltage is 300 or less and the roof area is guarded or isolated, that's 3 feet. And that comes into play in the city of Chicago a lot. Termination of through the roof raceway or approved support above the overhang portion of the roof that is less than 4 feet, and this is kind of what I was trying to draw earlier, that can get within 18 inches. Sides, important to catch this word. From the sides of doors, porches, decks, stairs, ladders, fire escapes, and balconies, and from the sides and bottom of windows, that's 3 feet. So you can have these wires going over the top of those windows. That doesn't matter if they're bare. And we're not talking about stuff that's in conduit. We're only talking about the actual wires themselves. All right. But anything else, if it's going left, front, right, below 3 feet of a window, then that's an issue. And you shouldn't be able to touch them. All right. So if you're standing on a deck or a porch or something, you shouldn't be able to reach out there and hang your laundry on them either. Right. So here we got a balcony, basically. I know it's a little bit blurry, but there's I think there's a doorway that comes out of there. So two things. Here's our service wire here, and it looks like it goes in front of the window. And then I'm sure we're less than 10 feet over that walking surface. And now here's one of our home inspectors. God bless his soul. And he's up there, and he can go ahead and hang his laundry on that electrical service drop. Obviously, it's going to be within 3 feet, and I would definitely document that one as well. And it's not, whether somebody does something with what we document or doesn't do something with what we document, that's their call. It's going to end up being their house. They're the king of their castle. They can decide to do whatever they want to do. But if somebody else comes in there, and let me back that up again, if I don't tell my client that that's too close and somebody can get hurt, then another electrician's going to come in here and want to sell them a repair to that. And guess what? They're going to end up wanting to charge that client to go ahead and move it. And the fingers are going to be pointed at me. And it's amazing how fast those fingers come out. I don't want to let someone else's problem become my problem. I know the rules. I learned them. And we should all know these rules. So go ahead and document it, and then whatever the owner decides to do is going to be strictly up to them. Going through trees is also an issue. I just document it. It's not that they have to cut the trees or move anything. But if the wires are running through them and the branches are going to be waving in the wind, especially when there's storms, I don't want them angry at me in case they lose power. One of the questions I get asked quite a bit is what belongs to the electric company and what belongs to me as the homeowner. All right. And that's where some of these lines come in here. So these are the power lines, also known as the service drop. All right. That's the red. The orange, these are the connections. I refer to them as the splices. And that's the line in the sand. Anything that is to the pole side of those splices belong to the electric company. Anything not including the splices that goes towards the house belongs to the homeowners. The white here is pointing at the service entrance cables, and that's what's going to be coming down to our meter and coming into the house. All right, this is an old gooseneck, what they're pointing at here, and then our service mast is what the blue arrow is pointing at there. Service drop, service point, again, that's where the electricity is coming in. We can see our splices. Notice they put insulation on the energized conductors, but there's no covers or insulation on top of the grounded current carrying conductor or the neutral or the messenger cable that comes in there. That's not a problem. That's actually normal, all right, that they come in there. But the other two should be. Now, here in our area, we have a problem with electricians upgrading systems, not getting permits. And then you see this all gobbed up with electrical tape on the currents, on the conductors there. I call that out. If they're not going to go ahead and get the permits and so forth, then I'm not going to let that problem become my problem. The attachment point or the service point, again, this needs to be secured to the house. This is what supports everything that comes in here. So on this one, it's right here. And then on the left-hand side, I never erased it, the arrows, but that's right over here. Again, the connections that come in here. But now, and this was, I took this picture, I remember it. This was a commercial property. And, even though we don't have to determine voltage anymore, excuse me, I still want you to be able to recognize three-phase systems as they come into the building here. And on this one, there really is no protection where it comes in here. So, red arrow 1. That's an energized conductor. Red arrow 2, energized conductor. Red arrow 3, energized conductor. And then this is our neutral, or our grounded current carrying conductor. So whenever you see 3 energized conductors and one neutral, so a total of 4 wires coming in. That's a 3-phase system, all right? If we look at the little box over here on the bottom right-hand corner of the screen, we only have 2 energized conductors. And then this one here is my messenger cable. That's my neutral. So I have a total of 3 wires. 2 of them are energized. One of them is the neutral. These are not required. Or I'm sorry, these are not 3-phase systems. They're single-phase systems. And that's where we get that 12240 from. Points of attachments, we need to be secured. Our service mast needs to be secured. I would document anytime you see these things are loose. All right. This one's kind of a no-brainer. I mean, for crying out loud, they put jumper cables on there, you know, to hold it. As happy as I am that people donate these pictures, I almost wish we could get them to us in high definition so they're not so blurry. But there's definitely something going on here. This is an easy defect to comment on. The drip loops, sometimes the service points of attachments come loose or break loose, and then the wires go straight. The problem with this is if water from rain comes in here, they're afraid it's going to come down the service mast and create a problem. And that's the whole purpose of these drip loops. All right, so as water comes down here, they're going to drop off and not come into the electrical system. This one's standing pretty free. You know, it doesn't look like it has too much of support going into the building there. And it actually looks like the wires are going over the roof on the right-hand side. So whenever something's super tall, you know, I mean, we can always look at the house and try and determine how long it's been here. But if that mast is starting to bend, then obviously we need to have something what's called a guy wire, all right? So, and that's spelled G-U-Y, guy wire. And that would be something that's going to go ahead and attach back to the roof just to give us some counter strength so it doesn't bend or damage the service mast coming in. Flashings, you know, I see this on re-roofs a lot. They don't bump it up properly or they don't have the right type of flashing in there. So what do? You get a bucket of tar and schmooey it all over the place, which is fine. It'll keep water out for a year. You might even get 2 years out of it. Who knows? But eventually that's going to dry up and water's going to be coming in. So again, if you see that it's not flashed properly, don't let somebody else's problem become your problem. Just take a picture of it and document it. Those service masts need to be secured to the wall. No ifs, ands, buts about it. All right? I'm kind of, like I said, one of those big dummies. I put my hands on everything. And I'll grab that mast and I'll give it the old wiggle. And if it's moving, it gets videotaped and it goes in our report. No ifs, ands, buts about it. That should be secured to the building. All right. SC cable. SC stands for service entrance. And this is where we're not using a service mast or conduit to run it through. All right. But again, all that should be secured to the building. It shouldn't be just flopping loose. And they're talking mostly about this area all up in here. All right. Again, service entrance cable. You know, it's nice to be able to read these cables so that you can determine, you know, how big the conductors are that are inside of them. I mean, I guess you could take a guess at it, but for me, and I'm going to show a slide in a little bit, there's really 5 things you need to know to properly determine the amount of amperage and if it's safe. Number 1, which we do have to document in the SOP, that's going to be the main disconnect rating or whatever's printed on there. But we also need to know the size of the wire, the rating of the meter panel, the rating of the disconnect panel that comes in there. You know, we mentioned the wire itself along with that breaker that we mentioned at the very beginning. So this one's attached to the brick. All in all, it doesn't look too bad as long as it's nice and sturdy coming in there or secure to the building. That's all I'm carrying. This cable, you know, and again, they're telling us it's every 30 inch. This is that writing I was talking about. So here it says SC cable. style type, but it's kind of worn out. You know, what size it is and the type of material that it is. And we're going to want to have those things memorized. And I'll get to a chart on that in a little bit. All right. So service drops, again, overhead. Service laterals, they come underground. All right. Our transformers, they're going to knock the power, or knock the voltage, I should say, down to 120 or 240 if I used both conductors or both legs. Anything that goes up and down is called a riser. So believe it or not, this is also a riser. All right. The lateral is what's underground here. And then we go to our meter, and our meter panel is the rectangle. We're not worried so much about the meter itself. We're worried about the panel. And then the first, we need a rating. We need a rating for the meter panel and a rating for the main disconnect panel. All right. And then they're showing our GEC and so forth. Just another view. Here they came underneath with a burial cable, depending on how deep you go. Sometimes it has to be in pipe. Sometimes it's free just to be a bare wire. All right. But again, it all depends how deep you go. But we're not going to know how deep those wires are. This is a commercial property, and they were using a lot of PVC for the conduit. And what's nice about the PVC underground is that it doesn't rust, it doesn't corrode, it doesn't rot, basically, which is cool. That's always a good bonus. But the bad thing about it is it also doesn't conduct electricity. So in conduit systems, we actually use the conduit itself for our grounding system so that it actually gets energized if I have a ground fault that happens. So whenever I'm dealing with PVC conduit, since it does not conduct electricity, I still have to pull a ground wire inside this conduit. I can't just pull my normal wires as I normally would. Above ground connections as it comes into the house. This is, again, nothing should be loose. Everything should be tight and secured, no wiggles. And I hear people saying that, well, yeah, of course we don't want that coming apart. That's going to cut the wires and it's going to short it out. Well, it's more than that. Is if those wires do come loose and they touch and energize this, there's no way to get that back to trip the fault. A lot of people don't realize that if I energize this portion here, it's not going to trip the breakers. I'm not getting power going through the main disconnect. And I'll talk more about that when we get to grounding and bonding and what we're looking for with those items as well. All right. Typical service lateral and a damaged conduit on the right side. Electric meters and bases. Now, these are usually going to have tamper tags on them. And that's what this is right there. All right, so we're not going to be able to open that up and look and see what the rating is on it. So, we're going to make some assumptions when it comes to certain things. I just had a call back today, right before I started doing this recording. And one of our guys told our client that, they might want to think about upgrading the electrical system. All right. So they spent $1,500. They really thought it was a good idea. They spent $1,500 and they went from 100 amps to 200 amps, right? And how much that was really needed, I don't know. I was going to have a talk with our guy just to see what he saw on that. But what they didn't do was upgrade the service entrance cables. They did not upgrade the conduit that's coming in here. They did not upgrade the meter panel, and they didn't even cut any of those tamper tags, so they couldn't get in there to change the wiring in the first place. So we may have actually made a problem worse when I start thinking about this, because if you end up putting a meter panel inside the house that's rated for 200 amps, but you're only feeding it with wires that are rated for 100 amps, you're going to allow 200 amps to flow through something that's not designed to carry 100 amps. So knowing all the things that have different ratings on it, to me, is important. And figuring out these 5 things to see if something's safe is also an important thing. So this is just something out of the old history books right here. These round meter bases, and again, we're talking about the panel, not the actual meter itself, all right? So these old rounded meter panels, those were typically rated for 30 amps. All right. You'll still see some more modern ones. They may be 60 amps, but we're just not quite sure. And the only way to tell is to get hold of a data plate. Now this one was nice, even though it's blurry, but this one actually had the data plate on the outside, so you're able to tell it. The newer ones, they're all going to be listed on the inside, so we're not going to be able to see it. All right. So let's talk a little bit about reporting amperage. Again, according to NACHI, the only thing we're required to do is to document what's listed on the main service disconnect. In this case, it's 100 amps. All right. But I got to share, I'm a big advocate. I want our guys to know more. If this is 100 amps, but yet I'm feeding it with a 10 gauge wire, that 10 gauge wire is only good for 30 amps. I should be able to recognize that and inform my client that even though this says 100 amps, it's really only a 30 amp system, but I'm going to allow 100 amps to go through it, which makes it a dangerous situation. All right. Again, the more we know, the more we're worth, and people rely on us when they buy their homes. So development in the early 1900s, they were looking at 30 amps in houses. From the 30s and 50s, it was common that they were 60s. After World War II, it was kind of common practice that it was 100. Nowadays, you're looking at seeing about 200 amps. And then even with all the new electric cars, those are going to be 60, 80 amp chargers on some of those things. If somebody wants to power their car up pretty quick, they're going to need like 400 amp services coming into the house. So you're going to start seeing bigger electrical services that are going to be entering the homes. But in all reality, like I live in a gas area, all right? So my furnace is not electric. My furnace is gas. So I don't have to worry about the electricity I need to go ahead and heat my home. My stove is gas. My dryers are gas. I don't have any real electric appliances in here. Everything I have in the house is pretty much all LED bulbs that comes in here. So the only time I'm really using any sort of larger amount of electricity is when my central air conditioners are going, and they're both 2.5 tonners, so they're both about 25, 20 amps that go in there, and even if both of them are running at the same time, that's 50 amps, which is nothing to a 200 amp house. And quite frankly, it's really nothing to a 100 amp house. All right. So I don't really take too much of these electrical services as a big deal. But if somebody wants to start getting kilns, electric dryers, electric furnaces, then we got to start taking a lot of that stuff into consideration. Know your area, I guess, is all I'm saying here. I'd like you to screenshot this one. I do not believe it's in the NACHI library. I'm going to mention it to them if they want to put it in there. So there's 5 things that we should be looking at in order to determine what the amperage is inside of a house. First and foremost is going to be our main disconnect. We saw that in the picture, and on the one that we saw that was rated for 100 amps. The next one is going to be a meter panel shape, all right? Well, we're not going to be able to get access to the inside to see the data plate of these meters, so we're really not going to know. So this is nothing but rule of thumb, all right? This is not black and white. This is not guaranteed, where it's written on there, but this is still a pretty good rule of thumb, all right? And in our areas, I also want you to assume these could actually be 30 amps. It's common that these are 60. It's very common that these are 100 amps when they come in here. And then the bigger one, I haven't seen one less than 200 amps yet, all right, where it comes to it. So I take that into consideration. So let's say we had this square A box right here. So that's going to be meter panel shape. And let's say that that's 60 amps instead of 100. The disconnect panel rating is going to be found wherever the main disconnect is located at. It's either going to be on the dead front cover or off on the sides. I like to take a picture of that and see what that's rated at. But let's say that was rated for 150 amps. Comes in there. The service entrance wire size, we should be having those memorized. Let's just say it was a number 2 aluminum that came into the house, which is a very common feed. A number 2 aluminum in this area is good for 100 amps. All right. And then the service entrance pipe size, that's what this charge. This is accurate and this is a science. So let's say this is a 1 inch and we're showing that it can go up to 100 amps. All right. So we look for the smallest number of the 5. The smallest number is going to be 60. All right. And that 60 amps is going to be what my amperage is. However, we're going to allow, because the disconnect allows up to 100 amps, we're going to allow 100 amps to flow through something that's only designed to carry 60 amps. That's not safe. All right. Now, if we go ahead and we use the 100 amps on here, and then this is now 100 amps, well, 100 is my smallest number. 100 is also my main disconnect. 100 is my amperage, and it's safe. I hope that makes sense. Typical meter installations, we usually find them on the outside. I'm just going to flip through a few pictures here. So these are the old round meters. Like I said, they're going to be either 30 amps or 60 amps. The old A boxes is what we call them. We have a lot of them in this area that are designed with 60 amps, but they can go up to 100 amps. All right, but again, without getting inside, we're just not going to know. The rectangular ones, we find this on 100 amp services a lot. But we've run into these rectangular ones. Again, they go up to 200 amps. All right. Typical meter installations. Again, here we're showing a 200 or 100 amp panel, on the left and an old 60 on the right-hand side. So depending on, if it's primary backup or townhouses and people upgrading is what you're going to end up finding. This is a 400 amp service next to a duplex is what we call these things. So there's 200 amp disconnects, one on each side. And again, totally acceptable where it comes in there. If you're not familiar with the wire sizes, I'd like to encourage you to go ahead and screenshot this one. All right. I do not believe that this is the chart is found in the Nachi education slide. That's where I got this information from, but it's not. You're not going to find the actual diagram there, all right? But there's nothing wrong with you going ahead and taking a screenshot of it now. So the common stuff that we're going to run into is going to be 200, 100, and 60, all right? So knowing these numbers for copper, 6, 4, and then in Chicago, don't ask me why the state of Chicago is more. But Chicago, they want it to be a number 3 copper. And then here as well, we're going to see, and again, it's 2/0. And that's how we pronounce it. So 1/0, 2/0, 3/0, 4/0, and then we get to the KCMs. If it's aluminum, you're going to see that the wire, when I go down in numbers, it's actually a bigger wire, all right? So a common feed here in Chicago is going to be a number 2 aluminum. And then I haven't really seen a 4/0 for 200 amps yet, but I'm sure that it exists, all right? And aluminum is about 25% the feed of copper. So I find that a lot of people still like to run with aluminum wires. All the wires that run pole to pole overhead, they're all pretty much aluminum. There's no way they could spend all that money in copper. All right. So I'm going to stop right now and just take a short break. And then I'm going to continue on again in a little bit.